Usually when we talk about a medical diagnosis, there's this expectation of um, precision.
Right. It feels almost like engineering.
Exactly.
Yeah.
Like you break your arm, the x-ray shows a jagged white line, and the doctor just points at it and says, there it is.
Yeah, it's visible, it's binary, and honestly, it's comforting.
We really prefer our biology to be easily categorized like that. A structural failure that we can just see and immediately understand.
But then you step into the world of elite sports,
Oh, yeah.
specifically non-contact muscle injuries, and suddenly that x-ray machine is completely useless.
It really is. We're looking at a diagnostic landscape that is just incredibly murky. I mean, you have a player running down the pitch, nobody touches them, and suddenly their hamstring just gives out.
Right.
And the question is always, why then? Why that exact sprint on that exact day?
Which is the million-dollar question.
Literally. So to answer that, we're unpacking a really groundbreaking new piece of research today. It's titled Enhancing Sports Injury Risk Assessment in Soccer Through Machine Learning and Training Load Analysis.
It's a fantastic paper.
Yeah, it was authored by Theodoros Tsilimigkras, Ioannis Kakkos, George K. Matsopoulos, and Gregory C. Bogdanis. And it was just published in the Journal of Sports Science and Medicine in September 2024.
And, the stakes here go far beyond just a single game.
Oh, for sure.
Non-contact injuries are just devastating for athlete welfare. They completely disrupt team dynamics, and frankly, they cost clubs millions in lost playing time.
Which is why this is so important. We're setting an accessible but scientifically clear tone today, because this isn't just about sports. It's about data analysis, biomechanics, and physiological overload.
Right, because for decades, sports medicine has been trapped in this reactive cycle, treating the trauma after the muscle fibers have already torn.
And moving from reacting to injuries to actually predicting the precise moment they're about to happen.
That is the holy grail of sports medicine.
Absolutely. And doing that requires moving from the abstract concept of, an injury to the very specific raw biometric data being generated minute by minute on the field.
You have to know exactly what the body is experiencing.
Right. So the researchers in this study built this incredibly robust baseline. They followed 25 professional male soccer players.
From Asteris SSSFC?
Yeah, in the Greek Super League. And they specifically isolated players who suffered a first-time non-contact muscle injury. So like hamstring strains, calf strains, adductor issues.
Which is key, because you want to eliminate the variables of past trauma.
Exactly. And they tracked every single movement over a massive 4-year period.
I mean, that scale is wild. That involves 665 training sessions and 111 official games.
It's a mountain of data.
It really is. And to make sense of that sheer volume of movement, the researchers divided the data into two distinct categories, right? External training load and internal training load.
Okay, let's unpack this. Because external load is fairly intuitive. It's essentially, it's like checking a car's speedometer and its odometer.
Oh, I like that.
Right, like how fast the car went and how far it traveled.
Yeah, exactly.
But the internal load is more like checking the engine's RPM and the internal temperature gauge. It tells you the physiological cost of achieving that speed and distance.
That is a great way to look at it. So for the external load, the researchers captured that using GPS units and accelerometers.
The ones they wear between their shoulder blades, right?
Yes, exactly. And they tracked total distance covered, the number of sprints, accelerations, decelerations, and the specific distance covered in high-speed running.
So that's basically the mechanical, biomechanical work the skeletal structure is enduring.
Right, but just knowing the mechanical work isn't enough, which is where the internal load comes in.
The engine temperature.
Exactly. They track this using continuous heart rate monitors, and this is where we elevate past the simple car analogy and get into deep physiology.
Because they didn't just look at average heart rate, did they?
No, they calculated a specific training load score.
Okay, what does that measure?
It quantifies cardiovascular and muscular stress. And alongside that, they track the exact number of seconds a player spent with their heart rate in the 80 to 90% maximum zone.
And the red line zone, right, the 90 to 100% max.
Exactly, the critical red line zone.
Okay, so having all those metrics, knowing the speed and the physiological cost, it gives you a great snapshot.
It does.
But a snapshot doesn't predict an injury. I mean, the danger doesn't happen in a vacuum. It happens over time.
Right. Having all this data is useless if you don't know when the danger occurs.
Exactly.
Right.
So the researchers had to structure this data temporally. They focused on a 28-day pre-injury epoch.
Basically the 4 weeks leading right up to the muscle tear.
Yeah. And they compared it against a baseline 28-day non-injury epoch for that exact same player.
Right, they were looking for the divergence, the exact moment the internal and external loads started pointing toward a breakdown.
And to find that, they used two specific metrics of overload.
Right, let's get into
So
those.
the first is DEV, or the deviation of maximum from average.
Which looks for an acute, sudden surge on a single day.
Right, like a massive, totally uncharacteristic spike in exertion.
Yeah. And then the second metric is ACWR, the acute to chronic workload ratio.
Okay, explain that one.
It compares what you did in the last 7 days, the acute load against your average workload over the previous weeks, which is the chronic load.
Got it.
The ACWR is heavily relied upon in sports science because it supposedly tells you if you're ramping up your training too fast.
Because if your acute load is vastly higher than your chronic base, your tissue hasn't adapted and you're at risk.
Exactly.
But, I'm looking at how ACWR is traditionally calculated, and there seems to be a massive mathematical trap here.
Oh, you caught that.
Yeah, because you divide the acute 7-day load by the rolling 4-week average, right? But if I have a hellish redlining week right before I get injured, and you drop that massive week's data into the 4-week average denominator,
Yep.
wouldn't that actually hide the spike? I mean, I'm just inflating my own baseline.
That is exactly the problem.
It's like grading on a curve where the anomaly ruins the average, and suddenly the dangerous week just looks like business as usual.
And the result of that business as usual illusion is that traditional injury prediction models often missed the warning signs completely.
Wow.
Yeah, you've identified a statistical flaw called estimator bias.
Estimator bias.
The extreme values of the injury week artificially pull the chronic average up, completely normalizing the danger.
So how did this study fix it?
Well, they applied a really crucial mathematical correction. They deliberately excluded that final week, the acute injury week, from the chronic average denominator.
Oh, that makes so much sense.
Right. They only compared the acute week against the stable, typical training weeks prior to the surge.
So by untainting the baseline, the acute spikes became starkly visible. Okay, so we've isolated the acute spikes from the chronic baseline. But wait, player A's dangerous spike is player B's standard warm-up.
Very true.
I mean, player A might regularly cover 10 kilometers a game while player B covers 7. If everyone's physiological threshold is completely different, a standard mathematical average or a generic cutoff point is totally useless here.
Which is exactly why traditional cutoff points fail.
Right, so how do you actually spot a pattern when the baseline is constantly shifting based on the individual?
Well, you bring in an algorithm capable of handling highly individualized, multidimensional variables.
Machine learning.
Exactly. The researchers deployed a specific type of machine learning, a support vector machine, or SVM, classifier paired with a radial basis function, or RBF kernel.
Okay, let's break down how that actually works, because it seems like the core of why this study succeeded where others failed.
It really is. So what's fascinating here is that a standard linear algorithm tries to draw a straight boundary line between two groups of dots on a graph.
Like, say, safe days on one side and injury days on the other.
Right. But human physiology doesn't plot neatly on a flat piece of paper. The relationship between running speed, sprint distance, and heart rate over a 28-day period is incredibly complex.
It's not a flat 2D graph. It's more like a sprawling topographic map with mountains and valleys.
That is exactly it. And the radial basis function kernel essentially acts as a mathematical warped space.
Okay, warped space. I like that.
If you can't draw a straight line through the data on a flat surface, the RBF kernel lifts the data points into a higher three-dimensional space based on their similarities.
So imagine grabbing that flat map and pulling it upward to create a landscape.
Yes. Now, the SVM can easily slide a flat sheet, a hyperplane, right, between the elevated injury peaks and the safe lower valleys.
Oh, wow. And the researchers didn't just assume this topographic approach was the best method, right? They actively tested it against other prominent models.
Yeah, they tested it against k-nearest neighbor and random forest algorithms.
But the SVM with the RBF kernel significantly outperformed them.
It did. Because random forest just looks at decision trees, if this, then that.
Right. Very rigid.
But SVM RBS evaluates the intricate, continuous relationship of all these variables at once, customized to the individual's unique physiological signature.
It literally learns the specific terrain of that particular athlete's body.
Exactly. And the algorithm's performance speaks for itself. It achieved an overall accuracy of 0.78 or 78%.
Which is huge in this field.
It really is. It had a sensitivity of 0.73, meaning it was highly effective at correctly identifying the actual injury epochs.
And a specificity of 0.85, ruling out the baseline, safe epochs.
Right. In the unpredictable realm of elite sports, those are incredibly robust numbers.
Seriously. I'm looking at the initial inputs, though. The machine learning framework started with 18 possible features, right?
Yeah, 9 metrics each for the DEV and ACWR calculations.
So if the AI is really as smart as we're saying, what did it actually strip away? What did it determine was the real signal cutting through all that biometric noise?
Well, through a rigorous selection process, the algorithm discarded the noise and narrowed the field down to 7 prominent estimators of injury.
Okay, what were they?
3 of these came from the the DEV, or single-day deviation metrics. These were the sheer number of sprints, the overall training load score, and the time spent with the heart rate in the 90 to 100% maximum zone.
Wow, those 3 are intense. They represent a sudden, violent physiological demand in a single 24-hour period.
They absolutely do. And then the algorithms selected 4 features from the cumulative side, the ACWR, or 4-week buildup metrics.
The chronic load.
Right. These were total distance, high-speed running distance, sprint distance, and again, the overall training load score.
Okay, so the algorithm flags these 7 features. But so what does this all mean?
Well, the real breakthrough of the study isn't just the math, it's what these specific features tell us about human biology.
Because this was the very first study to successfully include internal heart rate-related variables in a machine learning injury risk model, right?
Exactly. For decades, sports science has leaned heavily on mechanical load. Just how many miles did the player run?
It's a very structural view of the body, like
Right.
assuming the muscle is just a piece of fabric that tears when you pull it too many times.
Right. But by proving that internal heart rate-derived metrics like time spent redlining at 90 to 100% of maximum are critical predictors of muscle tears alongside mechanical load, this study entirely shifts the paradigm.
It's not just wear and tear.
No. Non-contact muscle injuries are not merely structural failures. They are the result of severe physiological and metabolic overload interacting with mechanical stress.
Okay, let's connect these 7 features causally because the mechanism here is fascinating.
Let's do it.
You have the cumulative variables over 4 weeks, total distance, high-speed running, sprint distance. That is the mechanical stress.
Right, the repetitive impact.
And over a month, that high volume of sprint distance slowly degrades the collagen matrix of the hamstring. It creates microtrauma.
Yes, the tissue is slowly losing its structural integrity.
But the tear doesn't happen during a light jog. The algorithm showed us that the injury triggers when that cumulative structural weakness collides with an acute DEV spike in the 90 to 100% heart rate zone.
Exactly, because when you hit that redline heart rate, your body's relying heavily on anaerobic glycolysis for energy.
Okay, what does that mean at the cellular level?
Think of the muscle fiber like a factory supply chain. When the factory floor is operating at 100% capacity, it produces a massive amount of metabolic waste.
Like hydrogen ions, lactate, all that stuff.
Right. And the workers simply cannot clear the waste products fast enough.
So the environment inside the muscle literally becomes acidic. The metabolic clearance completely fails.
And when that metabolic environment becomes toxic, the muscle loses its elastic return.
Oh, wow.
Yeah. During the eccentric phase of a sprint when the hamstring is lengthening, while simultaneously trying to contract and slow the leg down.
Which is a huge amount of force.
It is. And those metabolically choked muscle fibers physically cannot fire and relax with the necessary microsecond precision.
Because they're drowning in waste.
Exactly. So the compromised structural matrix meets the metabolic failure, and the tissue violently tears.
And the injury is literally the explosive intersection of a structurally fatigued bridge and a massive, sudden surge in traffic.
That's a perfect way to describe it. And for sports scientists and coaches, understanding this specific mechanism provides highly actionable intelligence.
Right, because now they can see it coming.
Exactly. If a player's continuous data shows a rising ACWR in high-speed running over the last 3 weeks, combined with an acute DEV spike in their 90 to 100% heart rate zone today.
The coach knows with 78% certainty that a catastrophic metabolic and structural failure is imminent.
Yes, they can pull the player back, alter the training load, and allow the metabolic waste to clear before the muscle ever snaps.
It fundamentally changes the job description of a sports medical team, from treating symptoms to managing predicted thresholds.
And the beauty of the SVM-RBF algorithm is that it adjusts those thresholds automatically based on the player's unique physiological map.
That is just incredible. And, even if you aren't managing a professional soccer team, if you're managing your own training, understanding this acute versus chronic workload rule is vital.
Oh, absolutely.
Whether you're prepping for a half marathon, lifting heavy, or just trying to stay consistently active, your own body obeys these exact same biomechanical rules.
No, all the same biology.
Right. A sudden surge in intensity layered over weeks of accumulating microtrauma is the universal recipe for a breakdown.
It really is. And, it raises a profound question about the broader applications of continuous biometric monitoring.
What do you mean?
Well, if an algorithm can predict the exact moment a professional athlete's hamstring is about to literally give out, just by analyzing invisible multidimensional variations in their heart rate zones and running speed over a 28-day period,
Yeah.
what else could this data reveal? What could these same wearable metrics predict about our own daily physical breakdowns or even systemic psychological burnout weeks before we consciously feel the symptoms?
Oh, wow. That is a wild thought.
Right. The signals of our own exhaustion are flashing in the data long before we register the fatigue. We just need the models to translate them.
The warning signs are literally already on our wrists.
Exactly.
Well, to explore the exact methodology, the mathematical formulas of the DEV and ACWR calculations, and the complete feature sets we discussed today, we highly encourage you to read the full article in the Journal of Sports Science and Medicine.
It is an essential read for anyone operating at the intersection of data science, biomechanics, and human performance.
Absolutely. Make sure to follow the channel and turn on notifications so you never miss our future deep dives into the latest scientific research. Next time you feel the urge to push through that extreme exhaustion, remember the factory floor. Clear the waste before the system breaks.